Hi folks, and welcome to SOPs and DOPs Part 2. If you didn't watch the first part, then a lot of this won't really make a whole lot of sense. Actually, what we're going to cover today is quite a bit simpler, I would say, than what we did last time, even though the outcome is going to look quite so different. So last time what we had done was we basically set up this constraint network where we generated geometry and we generated constraints on the fly here. So we generated all these little boxes and little links between them that would sort of jostle, and we did all of that in DOPs. So if you haven't seen that, go ahead and check that out in part 1. What we're going to do today instead is look at spawning some fractured geometry here. So what we'll do in this case is we'll show how to basically spawn into a simulation fractured geometry on the fly and bring in all of the constraints that needs. So we're going to work on this one today. So again, we're going to start from scratch, so I'll just make a new geometry here. Going to toggle off that old version, and we'll call this Fractured Tutorial. Okay, so we'll dive inside. So the first thing we're going to need is something to fracture. We'll just start with a basic box. There are all sorts of tutorials out there about fracturing. I'm not really going to get into this in any great detail. We're going to do the most basic version of that possible, because the focus for today is really about setting up the SOP solvers inside of DOPs. So to get a fracture, we're just going to do an ISO offset. That's going to turn this into a volume. I tend to like to bring up the sampling divisions. The default gives kind of a fairly fuzzy shape, so you get much better definition with sort of higher sampling divisions here, so we'll do that. We will scatter a few points in here. This is way too many for our purposes. I'm going to do something nice and small just so we can get reasonable simulation times. For fracturing, I tend to like to turn off all of this relaxation. I like to have it a little bit more clumped up. That gives you some smaller pieces, some larger pieces. But again, that's a little bit outside of scope for today. And then we're just going to drop a Voronoi fracture here. Oops, don't need to dive in there. Okay. I'll pipe that in there, turn that on, and sure enough, we get a nice fracture here. We don't really need to change any of these settings right now. All of this is fine. I am going to change the name just for later on, and I'm going to call this box. And we'll come back to that a little bit later. Otherwise, all of this is fine. So this gives us our fractured geometry. If we drop down an exploded view, you can see that we've got all of our nice pieces here. Everything looks great. So to bring that into the DOPs, we're again going to assemble, and we're going to create packed geometry here. And I don't actually want it to create the name attribute because we already had that straight out of this Voronoi fracture here. You can see that all of these pieces at the primitive level get a name. So they range from box 0 to box 31 for our 32 points. So we don't want to create a new name here. We want to keep that name. So I'm just going to turn this off, and what it'll do is it'll just promote that primitive name up to the point level, and here we go, box 0 through to 31. So that's exactly what we want. We do want to turn on packed geometry. That's critical. So after packing, we'll just drop down a null, and I'm going to call this geo. And then the last thing we want is constraints. And the nice thing about the newer Voronoi fracture methods is that if we just drop a null here so we can take a look at this output, these constraints here already exist. So Voronoi fracture gives us a basic connect adjacent pieces set of constraints. You can see it's got all the correct information because it knows about the names because it generated those names. Another reason we don't want to change those names in the assemble. So we actually already have these constraints. All that they're missing here is they don't have a name. So these constraints just by default have no type. So they won't actually work as constraints right out of the box, but they're just about there. So I'm going to call this con so we can import it. And then I'm just going to drop down a primitive wrangle. And we're just going to set the constraint name. So at constraint name. And we're going to do glue constraints, the sort of simplest constraint we have available. Okay, so that's pretty much all we need at the SOPs level. We've basically just set up a really basic constraint network for some fracturing geometry. So now we can dive into DOPs. So we'll make a basic DOP network, and we're going to set up another really simple, similar to the last time, bullet sim. So I'm just going to drop down the pieces we need. I'm going to want a ground plane right off the bat. I'm going to want gravity affecting this one. We'll just pipe all that in there. We're going to again bring in this rigid body solver. Pipe that in there. Oops. Hey, there we go. We're going to want some packed geometry, because that's the object we just made. And we're going to want some constraints. So I'll drop down a constraint network, bring that through. And finally, if I can connect these things right, we're going to need some kind of a constraint. And we'll use a glue constraint because that's what we called it. So we'll put that in there. So these are all the pieces that we need. We're going to see our solvers. We're going to attach a solver to the constraints and a solver to the rigid body on this post solve. And that will be pretty much everything that we're going to do in this network. So let's start assigning some things. Inside of our packed object, we need to point to that geometry we made. So we'll just grab that. So I'm just going to fracture tutorial, geo, accept that. So that gives us our cube. You can see it's embedded because we had it at the origin, and that's fine. We'll adjust that like we did last time. And then for our constraint network, again, we're going to point this to con. And that will give us that. And if you remember, we set the name to be glue here. So we want to make sure that our constraint on the glue constraint is the same name. So instead of this data name conrel glue, we're just going to set that to glue. Now, before we get into any of the rest of the solving, let's just make sure that this functions correctly. I'm going to actually turn off the ground plane. We know that it's there. I just don't really need to see it right now. It's not that important. So I'm going to turn that off so we can see things more easily. I'm going to undo this a bit later, but I'm going to start by kind of moving this up so it has a little bit of height. And we're just going to take a look at this. And I suspect this strength on the glue constraint is going to be too high, but let's just take a look. Yeah, I think we lost like a couple pieces at the bottom there, but that's not really going to fracture for us. Let's try dropping it from a little bit higher. And let's drop this strength by at least half. Let's take a look at that. Okay, that might be a little more interesting. Yeah, we're still getting some nice larger pieces sticking together, but we are at least sort of coming apart. So I think that's going to work nicely for me. Okay, so this would be how you would set up like a really basic rigid body simulation. We're basically done at this point, but that's not really what we wanted to do. What we want to do is now take this and spawn these in over time. So we're going to go ahead and set that up. If you watch part 1, you'll probably be able to predict what we're going to do is we're going to do a little SOP network here. And the reason we're going to do it in a network instead of directly in a solve is because we want to modify both the the constraints and the geometry at the same time. So kind of within the same network, so everything knows what we're dealing with. So let's just go in here and we'll set up our inputs and our outputs. So we're going to want to merge in the current geometry and we're going to want to bring in the current constraints. And we're going to output our updated geometry. So updated. Oh boy, I can't type today. Updated geo, and another null here, or our updated constraints. Okay, so to bring in our geometry, we're going to all use absolute paths again. So we'll just go from object into our fracture tutorial, into our DOP network, which should be here. And once we're in there, we want to go to our, actually I'm going to leave this open so I can grab, because it's a long name, so it'll let me autocomplete there. Then I want the geometry. And you might remember if I do this alone, it's not going to like it. And that's because once we hit the .NET, this / needs to become a colon. We do that, and we get our geometry here. So that's perfect. So that's the geometry that's currently in the sim. So the first thing I'll do is just pipe that straight through, and we'll do something very similar here. I'm just going to grab this whole path, drop it in there, and you may remember from last time, if we go up to our .NET, just take a look at the spreadsheet. We find our constraints under, let me expand this, relationships, constraint network 1, and in fact, I'm going to save us a little bit of time here. I'm going to rename this. Let's just call it connet. So we go to relationships, so now it's called connet, and then constraint network, and finally we get to our geometry here. So we would go .NET and then relationships, connet, constraint, network, geometry. Oh, and I can never get this right. It's already upset with me. So what have I done wrong? Doesn't recognize that. Oh, connect. I want connet. There we go. And now we get our constraint network sitting right there. Perfect. So if I pipe that through into the updated constraints, now we can set up some basically non-changing SOP solvers. So we'll grab 2 SOP solvers. I'm going to pipe one into the constraint networks, and we'll pipe another one into the rigid body here. Both of these, we're going to want to use an external SOP here. This one that's attached to the constraints is going to be updating that constraint network, so we want to point it to our SOPNet updated constraints. And this one, which is going to be updating our overall geometry, our RBD packed object geometry, we're going to want to point to those updated geometry bits. Okay, there we go. Now I like to make it clear how these things are linked, so I'm just going to give it a little net box there. I'm also going to sort of recolor my constraint stuff. So I'll hit C, bring up the color tab. Let's say constraints should be a reddish color, and geometry, I'll just grab these two. We'll give that a nice, we want to differentiate from the rigid body, so let's give it a nice blue color. This is just to remind me, okay, this stuff is constraint stuff, this stuff is geometry stuff, and then here's my solver and all the extra stuff down below. Okay, so our SOPNet, let's just give that a color too. This is where we're going to be updating both of these things. So right now all we've done is basically just copy through. We basically grabbed the existing geometry and pushed it through. So if we were to run this now, nothing would change. We would get this one block and everything would simulate exactly as before. Perfect. Okay, so what we're going to do instead is we are going to do our old friend, the switch. And every so often we're going to bring in some new geometry and merge it with the old geometry. So we'll grab a switch here, and we will say if the frame mod some number, let's say every 10 frames again, equals 1, we're going to do something. Otherwise, we'll do nothing. And in fact, I'm just going to set this to 2 because as we covered last time, you start the simulation on frame 1, but it usually doesn't evaluate all these things. So instead of toggling like we did last time, we went in here and we said solve on creation frame. What I'll do instead this time is have it just update on frame 2. So that's another way to get around that. So again, on this side, we're going to be doing something. So every time we hit sort of a value that's 2, 12, 22, and so on, we're going to grab this second branch here. Now, a little bit of housekeeping or quality of life I'm going to set up this time. I'm actually going to give ourselves a parameter because we have these two switches. We're going to need the same switch to be over here on our constraints because we want to update at the same time. So we're going to have these two constraints. If we decide we want to switch this 10 or this 2 at some later time, we're going to have to remember every time and be really careful to make sure we change both of these switches at the same time. A better way is to set up basically a little controller here. I'm going to hit Z here to get some shapes. I'm going to give this a nice circular shape, give it a black color. I'm going to call this frame switch control. And what we'll do in here is we'll set up a new parameter. I'm going to go to this little wheel. I'm going to go to edit parameter interface. And I don't know why it's spawning off the side of the screen here, but anyway. And we'll make a new integer parameter. And this is going to be basically how many frames. What's the frame interval we want? So right now we're using 10. That's this number here. What we want to do is basically say, well, let's toggle that. Let's let that be something we can control on a little slider. So I'll call this spawn frame. Actually, I guess it should be spawn interval. We'll just call that spawn int, spawn interval, apply, accept. So now we get this little controller. We've got the slider. I'll set that to 10. And now here where we had 10, instead of putting that, we're just going to grab detail. Actually, this is not a detail attribute. We're going to do this is a channel. This is an integer channel. We're going to grab that from frame switch control, and we called it spawn int. So we'll just drop that straight in there, and we'll do this again, mod 2. Sorry. Equals 2. Oh, it says it doesn't like that. I think it probably doesn't. There we go. You would use CHI or CHF, etc. in wrangles. I think in the sort of input box format, it doesn't like you specifying those things. So just specify that it's a channel. So we'll grab that same parameter here, drop that in. If you click on this, it'll resolve to what it's sort of showing us. So it's 0 because we're not at sort of 2. If we go to 2, it becomes 1. And we can sort of, oh, it's upset for some reason. Everything's frozen. There we go. And if we go to here, we can just change this at any time. So we can set that to 8, and this will all sort of update normally. So if we went up to 10 now, that will turn on. Whereas if this had been 10 again, then this would be too soon, and this would be 0. So you can see that we can just change both frames all at the same time with this one switch here. Okay. So that's just a little bit of housekeeping. Now, what do we actually want to do on this secondary branch? Well, it turns out this is a lot easier than last time because our constraints and our geometry, we don't need to sort of be creating them on the fly. All we need to do is read them in. If we go back to our basic geometry here, these constraints are pointing to these pieces. We don't need to sort of do the same thing that we did in part 1 where we had to find a random piece and figure out where they both were and add those constraints there. All we really need to do is read in the geometry and read in the constraints, and then rename them to make sure that they're unique. And that's really the entirety of this setup. So it really is quite a bit simpler than last time. So we'll read in our geometry. We'll just do an object merge here. And we'll go back to this geometry here. So we're going to pull this in. And we're going to want to be merging this with our old geometry. Don't need this null anymore. And we just want to make sure that we rename these pieces. So if we look at this geometry we pulled in, this is our box sitting at the origin here. It's got all these pieces, box 0, box 1, etc. We're going to do the same thing we did in the last part. We're just going to rename these pieces, and we're going to add the frame. So we'll say asset name. We're updating a string attribute. We'll use sprintf again, and we're just going to do that same %s as a placeholder for a string, %d as a placeholder for an integer. And we'll pass in its existing name and the current frame. So if we pipe this through, then we end up with box 0 at frame 1 here. Of course, we're not actually going to evaluate on frame 1, but this solve solver, because we're in the context right now, is sort of showing us what would be happening here. Now over on the constraint side, we basically want to do exactly the same thing. So we're just going to go object merge, and we're going to bring in those constraints, con, and we're actually going to take this exact same renaming because we're going to iterate over the points. So if we look in this constraint network, the names are sitting on the points here. They're not on the constraints, the edges themselves. The edge just tells us the constraint name. So the names for the items that are being constrained are sitting on the points. So we're actually just going to use this exact same point wrangle, and we're going to rename it exactly the same way. And then we're just going to merge it with the old constraints. And so really all we've done here is we've basically taken our initial geometry and our initial constraints, and we've just read in new copies and given them new names. And that's all we really needed to do. Now, we could absolutely have done each of these in those separate solvers. So we could have done this out here and here instead of in this SOPNet. I like to do all of this stuff right in the SOPNet and use this external geometry because if you want them to start to refer to each other, then you can do that more easily here. You also have sort of just a single view of everything that you're taking control of. And we again get this nice controller right in the middle here. It just puts everything in one place. And to me, that just makes things a little bit cleaner. I like this way of doing things. Okay, if we were to run this now, it's going to be a little unhappy. We have this initial box that we've placed up here again. The first thing I'll do is actually get rid of that. And that means we can get rid of these constraints as well. We're just going to spawn things in. So on frame 2, this is going to spawn in. So if I skip to frame 2, we get our first box. You can see these constraints here. At this point, I'm just going to turn off the constraint visualization. So I'm on the constraint network here. I went to guide options. I'm just going to turn off that visualization. We don't really need it. This is sitting, it's embedding with the ground plane. That's not ideal. It's going to sit there and not really move. It's kind of jiggling around because it's intersecting. It's getting very upset. And now what's happened at frame 12 is we actually added another box that's sitting right on top of that old box. So we're not doing great here, but every sort of 32, 42, we're basically just stacking them on top of each other, more and more and more of these here. And that makes sense because we haven't given them any offsets, we haven't sort of moved them around or done any of that work. So that's really the only other thing we have to do is spawn them in sort of different new locations. So let's set that up. We'll go back into our SOPNet here. So all we did here was rename them. So let's add another wrangle. and we're just going to update their positions. So let's start and give ourselves a seed for a random function. We'll base this on the current frame. We'll just add some other value here just for the sake of it. So this gives us a seed. Now we want to generate a position. So I'm going to call this pose. I'm going to use the random function, pass in this seed. So that's going to give us a random vector with each component ranged from 0 to 1. I want to rescale that a bit. So the first thing I'm going to do, I'm going to multiply this by 2. Oops. Times equals. I'm going to multiply that by 2. I'm going to subtract 1 from each component. And then I'm going to divide it by 2 again. Okay, so what am I doing here? Basically what I've done is I've taken this value, which is from 0 to 1. We scaled it from 0 to 2. I subtracted 1, so now it goes from -1 plus 1. And then I divided by 2 to go from -0.5 to +0.5. And actually, maybe I don't even want that last part. So let's just scale this from basically -1 to 1. So it's going to spawn kind of in that range. And that's probably going to be a little bit tight here, actually. So let's take that whole thing and multiply by 5, for example. So now we're going to get a vector that's basically within a sort of 10 by 10 cube arrayed around the center here. I don't really want the y-axis to be random, though. So let's set that ourselves, and let's just set it at 5 for consistency here. So now what we've got is a position that's ranging. We started with just values 0 to 1. We scaled them up 0 to 2. We subtracted 1, so we got from -1 to 1. Multiplied, so we go from -5 to +5. And then we set the y-axis to always be 5. So now we're getting a plane that goes from -5 to +5 in x and z. And it's sitting all the time up at 5. So we can now set the position here. And I'm going to do plus equals. Actually, here, let me show you what happens if I just do equals. So what I've done is I've set the middle of this box. So if I just do at p equals position, we can just go back here, and I'll just show you at frame 2. All these pieces have ended up mashed together. And the reason for that is we're setting each of these pieces to be in that same spot. Now, we don't want that, because if we go back to when we first merge it in, each of these pieces has its own coordinate because it has sort of an offset from the center. They're fractured. They're separate sort of individual pieces. So this box is not a single box sitting at the origin. It's a whole bunch of pieces sitting around the origin. So we just want to add this position to its existing position. So we'll do plus equals. Now if I do that, and we skip ahead to frame 2, now we get a whole box sitting there. And that will start to fall down. At frame 12, we get a new one. At frame 22, we get a new one. And if we just let this sort of go through, you can see we're getting each of our individual boxes, and they're falling down and colliding. So as a basic setup, this is pretty much covering everything that we wanted. But there's a few things I do want to take care of just because this is nice and simple and straightforward. I figured I'd add a little bit extra here. So there's 2 things I want. 2 of them are just for the sake of appearance. They're just kind of fun. And one of them is actually pretty critical. And we haven't seen it here yet, but I can force it. Let's say we constrain this down quite a bit smaller. Let's say from -2 to 2. So I'm actually making this spawn area a lot smaller. So I'll just reset all of that. Now if we try this again, what we'll see, and there we get it right away at the second one. When the second one spawns in, so I just go to frame 12 here. When the second one spawns in, it's actually overlapping the first one. And, that can be kind of interesting. They start to fall together and sort of destruct in that way. But it's probably not what we want. So we're going to want some way to make sure that we're not getting overlapping when we spawn these items in. So let's go back in here, and let's figure out some way to set up this intersection. Now, if this box was a single point, this would be relatively easy. What we would do is we would take the sort of our candidate position, so we generate a random position here, and then we would test against all of the other points in the existing geometry and just make sure none of them are too close to it. And if they were, we would generate a new one, and we just keep doing that test. Now the problem with that is that we have a whole bunch of pieces in here, and we want to test those against a whole bunch of other pieces, and that just starts to get costly. You could write it, you could set that up in a detail wrangle, or in some sort of a point loop with sort of branching back, but it's going to start to get pretty costly. So the way we can get around this is to say, well, if it was simple for this to be a single point, let's just make it a single point for now. So we'll go assemble. And we're not going to create a name attribute, we do want to pack it. And what that means is we basically get a single point here. You'll see it's made its own name, we don't really care about that, that doesn't matter to us at all. What we've done is turn this whole box into a single point. Now we're going to take this wrangle here. I'm going to pull that out, shake that out. And we're going to pipe this in, and we're going to set the position on this one, and we're going to reference all the positions of the old ones. So what we're going to do here, we're going to sort of generate an initial random point, and I'm just going to sort of tidy this up. There we go. I'm going to declare the variable, and then I'm going to do the work on it. So we're going to generate this random point, and then what we want to do is find the nearest point in the existing geometry and test whether or not it's too close. So we're going to use near point, and we're going to check the first input here. So the second input, first index. So we're going to check the old geometry on that input, and we're just going to test this position we just created here. So that near point just gives us a point index. We actually want to know where that point is. So let's go vector near pose, and we'll just reference that point attribute on the near point there. The last thing we want is a distance, and this is just going to be the length of the vector that's between those two positions. So we generated a random position, then we found the nearest point in the old geometry to that position. We found sort of the position of that near point, because this is just an index, so we use that index to get the actual position. So now we have the nearest position in the old geometry to our current candidate position, and then we got the distance between those. And so what we want to do is, while that distance is too small, so we'll figure out what too small is in a second, let's just say 1. While that distance is too small, generate a new random position and do this test again. So let's just grab all of this. We'll drop that right in there. I'm going to go ahead and open this up. So I'm going to go to, I just did a right click here. We're going to go to expression, edit string. Grab all this and tab it over with this handy button up here. Okay, so what we're going to do is we're going to generate a new position and do that same test. And we'll just keep generating new positions. That was dist. We're just going to keep generating new positions until distance passes this test, until the minimum distance is larger than this value, whatever value we choose here. At that point, we'll save this position. And here, because we only have the one piece, we're actually just going to set it. We don't really need the plus equals anymore. Now there's one extra problem, which is that obviously this random seed is based on the frame plus 17. When we loop through this, that our seed hasn't changed at all. So the last thing we need to do in this loop is update our seed, and we can just add 1 to it. We'll just keep sort of bumping through the seed until we hit a point that's going to work for us. Okay, so once we've done this, what we've basically done is found a point that doesn't collide. So that's going to be great for us. And what we need to do next is simply reverse this assembled we did. Because what we did is we took in our full fractured geometry here, all of our independent pieces, and we sort of converted that to a single point. We collapsed that down, we assembled it and packed it into a single point. And we used that point for our test and updated where it fell and found sort of a nice position that's going to work for us. Now we want to unpack it back to its individual pieces. And we can just do this very, very simply. We don't need to sort of transfer anything. We don't need to transfer any groups. We've got box 0 through to 31 here. Everything is perfect. But now all of that is sitting in that position that we moved that whole packed geometry to. At that point, we can just pass it on through into here, and everything else should work just fine. So if I update this again, let's leave it at 12. We no longer get that overlap. It basically would have tried that position, found that it failed, and found a new one. When we hit 22, again, no collision. So even though we found a much smaller area here, we can keep spawning these in and they won't be colliding. And that's just generally a little bit better. We can avoid those collisions. So that's our final bit of sort of mandatory processing here, is dealing with that. The last things I want to do is just sort of gussy this up a bit, make it a little bit nicer, a little bit more interesting. One thing we can do is just add color to each of these sort of boxes. So what we'll do again is we'll basically let's just grab one of these random seeds here. We'll make something very similar. I'm just going to do it in the same place as the name. So we'll say that's our seed, and we'll give it some other value here. We'll add 22, and we're just going to say at CD equals random r seed. So now we're just going to give each of our boxes its own color. Now, if we watch it in DOPs, we're not going to see any of those changes. They're all going to look the same color. You may wonder why that is, and basically it's just not really processing those individual attributes on those points. So those are point attributes on the packed geometry. They're not really being read in. They're not being interpreted by the solver here. But we'll see when we unpack it, when we go back into SOPs to get our sort of final geometry for the render, we'll see when we unpack it that it will preserve all of that information. And in fact, let's just go out and do that now. So if we want to get this back into SOPs, we're going to use a DOP import again. I'm just going to alt drag that network here, and we want whatever the RBD object was. And we're just going to fetch that geometry. So if I do that here, and just scroll forward, we get a bunch of these boxes. So this is exactly what we saw in DOPs. And now if I unpack this, and make sure to transfer color. So we're going to transfer CD. There we go. Each block gets its own color now. So you can see that that information was successfully stored on the pieces. It just isn't being interpreted while it's packed. Now, if you color the pieces first, how do I want to show this? Yeah, let's just go here and let's just drop a color down at this point, and we'll just make it. We'll put it on the primitives, and we'll do a ramp from attribute, and we'll just say name. Sorry, I don't want a ramp. I want random from attribute. On name, if we go here, this is going to color each of those pieces independently. If we had passed all of that into the network, now you'll see that those colors will be preserved. So it understands everything that you put into the packed geometry in terms of these attributes. But if you add them inside, a lot of times it's not going to show up in the visualization until you unpack. So let's just get rid of that color node again. We don't want that in there. And we can see here, if we unpack it, we'll get that information again. So now each of these has its own color. Now, I'm going to do just a little bit of extra cleanup on that color. One thing that happens when you use random, because it's going from 0 to 1 on each channel independently on RG and B, you tend to get these sort of washed out muted colors. And that can be sort of nice, but I'm just going to give them a little bit of extra punch. I'm going to drop an attribute wrangle here, and I'm going to say, let's turn this into HSV format. So let's take our RGB, our red, green, blue, and let's turn this into hue, saturation, and value. So vector HSV equals RGB to HSV. It's got a handy function for that. And we'll just take the existing color. And what I'm going to do is I'm just going to set the saturation. So that's our second input, our 1 index. Hue is 0, saturation is 1, value is 2. And let's just set this to 1. So basically I'm just going to crank the saturation on each of these colors. And then we'll put that back in with HSV to RGB. So if I do that, we'll get these really high saturated, nice individual colors. And, you know, debatedly, this is uglier, but I kind of like to just make it a little bit punchier there. Okay, now the last thing I want to do actually is get sort of some different shapes in here. And there's a few different ways to do this. I'm going to do this the easiest possible way. It's a little bit clunky. You could do this inside DOPs, and I know everything we've been doing has been like, let's do it inside DOPs. So actually, yeah, let's do it inside DOPs. But the setup is going to be very similar anyway. So what I want to do is basically make several of these setups here. So right now I have the box. Let's say we want a sphere and a tetrahedron. So let's just copy this whole thing a couple of times. Here we go. And I'm going to make this box visible in wireframe just as a scale reference. And let's start with a sphere. I'm going to make this a polygon so it fractures nicely. Bump up this resolution a little bit. And we get a nice sphere. So spheres by default have a radius of 1. Boxes has a side length of 1. So a sphere is going to be about twice the size of a box by default. So we can just scale that down to 0.5. Now it's maximum extents, like it's fully bounded in here, but it doesn't really fill the space as much. So I'm actually going to say something like 0.6. I feel like that's a comparable size. I don't really care about exactly matching the area. I just want it to be visually similar. So I'll just swap that in here. And then finally, let's get a tetrahedron. So we can go to platonic solids. And there's a whole bunch of different options. Tetrahedron's the first one. Let's just use that one. Again, this is a little bit bigger than the box, but it also doesn't take up very much area comparatively. I think I'm happy enough with that size. So let's just leave the tetrahedron as is. Pipe that in here and here. Now, this is where my initial naming of box here became important because we want to differentiate these. So for the sphere, let's just call it ball. And then for the tetrahedron, I'm just going to make tet. So now when we assemble the sphere, we have sort of names that start with ball. When we assemble the box, we have names that start with box. And when we assemble the tetrahedron, we have all our names starting with tet. Now I'm actually just going to, this is how I want to do this. Yeah, I'm going to merge these together. We're going to add something else before we do that, but I'm just going to merge those all in. And yeah, and then we're going to grab all of these constraints and merge these as well. Let's drop that in there, grab this, and we'll grab this constraint as well. Just going to try to tidy this up a little bit. Let's bring all these assembles over here. So we're basically just taking those outputs from the Voronoi and funneling them into different places. So we get all of our geometry over here and all of our constraints over here. Now this alone isn't going to work terribly well. If we went back into our DOPnet, basically what we're going to do now is we're going to spawn in all three of these sitting on top of each other every time we hit that. If we just run, yeah, you can see that they're all clumped together. This is not quite what we wanted. What we want to do is sort of choose one of these randomly each time. So the way we're going to do that is we want to set up one extra sort of bit of information on here. And what I'm going to do, and this might not be, this is going to be a little bit clunky. Yeah, doing it at the SOPs level is a lot nicer. That's okay. That's okay. Let's do it at DOPs anyway. Oops, I don't want to blur. I just want an attribute wrangle. I'm just going to set point attributes on each of these things. So I'm just going to say I at, and let's call it shape. And we'll set the first one as 0. Paste one of these in here. This will be 1. And set this one in here. And this one will be 2. Then we want to do the same thing on these constraints. Let's just grab all of those. 0 here, 1 here, and 2 here. So we basically just set this shape parameter. And what we're going to use this for is we're going to set up a little random selector inside of our DOPnet, and we're basically just going to get rid of everything that doesn't match it. How I would have done this in SOPs is I actually would have put a switch at this level. I basically would have just picked one of these with sort of the frame driving a random selector. And that way, each time it drew from the DOPs network, it would be grabbing from that switch. It would only get one piece of geometry. But for the sake of sort of the principle of this tutorial, let's go through and do it in SOPs. So in here, what we want to do is right before the merge, basically, right before we do anything else after that, the first thing we want to do is actually pick what part of that that constraint information we want. And what I'll do here, let's just use another sort of selector up here. Oh, that's kind of unnecessary. Yeah, we'll just do it inside here. So let's go to an attribute wrangle. And what we're going to do is we're basically going to select which of these shapes we want to keep. And so we need some kind of a random value here. So let's go int r, let's go int shape. And we're just going to take random. We're going to pass it the frame as usual with some kind of an offset. Let's say 13. I'm going to multiply this by some large value. Call all of it an integer and go mod 3. So this is just going to select a shape for it. This is basically just going to give us a random value that's 0, 1, or 2. And it's going to be based on the frame here. So next what we want to do is just say if at shape does not equal shape, we're going to remove that point. And there we go. So we're left with just the tetrahedron here. Now we just want to copy this over and drop it into our constraints as well. Now if we get rid of both of the points, we're not going to be left with a primitive anymore. That primitive will disappear. So once we get rid of both the points that create the primitive won't be there anymore. So we've effectively done all of that deleting. Because we're using this same seed, we're going to get the same values. So when we delete sort of all non-tet objects, we're going to delete all non-tet shapes as well. And that's really all that we have to do here. So if we go back out, reset everything, go back to our unpacked and colored geometry here. If we turn this all on, we should get a nice mix of shapes. So we're getting boxes, we're getting spheres, we're getting tetrahedrons. They're all sort of coming out and not overlapping. We've got all of their colors, and all of this is looking pretty nice. All right, so that's all I wanted to cover in this part 2. You can see how we use a lot of the same concepts from part 1 here. We're basically going to sort of go in and we're going to handle our merging in of new geometry and our merging in of new constraints all in the same network, so we have a nice unified workflow. Whereas in the previous one, we had to generate those constraints sort of dynamically. We had to pick old objects and figure out how they interacted. In this case, we really just need to copy them in. And we added some extra logic to pick between different shapes and a little bit of a sort of reference to the old geometry to make sure we didn't have collisions. But actually doing something like this is quite a bit simpler than sort of that other version. So hopefully you find some of this useful, and I'll see what makes sense to do a tutorial of next. If you have any comments or any requests, I'm happy to entertain those. I'm looking forward to making more of these in the future. Thank you very much, and goodbye.